Okay, today we want to start talking about a little different topic, another aspect of controls we really haven't delved into too much. Most of the work that we've put into this topic up to this point has dealt with transient errors. How does the system respond when subjected to a step input? So we've got a step input in here, and then what does our system do in response to that? How quickly, how much overshoot does it have? How oscillatory is it? How quickly does it quiet down and reach a steady state value? And so this is an application that has widespread use, especially in systems that are moving and where we want to keep the system on a position value or an altitude or a pressure, and keep it on track as we move that position or altitude or pressure around. And so the transient is very, very important. But there's another aspect to controls that is also very important, and this is steady state error. Okay, in many systems, sometimes they're called follower systems. What we're most interested in is what happens not in the transient, but what happens in the steady state. So in the example of an oven, okay, we were not really concerned about how quickly your oven comes up to temperature. I mean, we'd like to have it come up to temperature relatively fast, but whether it comes up in 30 seconds or 2 minutes, we really don't care. What we're most interested in is, will it maintain that 350 degrees accurately over a long period of time? And so we're interested not in the transient, but in the steady state error. And so this is a whole thing that we need to talk about and figure out how we design a controller to work for that situation. Now, if we take a typical system, let's say just a first order system, we have a K and we have a 1 over 1 plus, or S plus 1, let's say, and we put a feedback element on here, and we're looking at the system. Of course, we know that the response of this is going to look like this, but what we really haven't talked about a lot is that our set point in here, I'm going to start calling it a set point, the value that we input here at the set point is, we're in this type of a system, we're never going to reach it. There's always going to be some sort of steady state error. Now, we can crank up the gain on this, and as we know from calculating our KDC, we can crank up the gain, and we can move this closer and closer to the set point as we crank up the gain. Okay, but what we do when we do that is we risk first of all, we're never going to get there. And second of all, what did I do here? And second of all, if we look at the root locus on this, we're going to run this out along the negative real axis, and what we're going to run into is the possibility of running into some high frequency stuff out here that's going to set off some oscillations or even potentially cause this system to go unstable. And so just cranking the gain up is probably not a really good solution. So if we step back just a minute and look at this, and what we're going to see is that we've got a thing happening in here. We've got this error, okay, a little bit of error. And the thing that keeps us from not converging on the set point is typically, like in a mechanical system, is the friction, or in a thermal system, the heat loss. We can't quite drive it hard enough to get past that point, and so we have this static error associated with this. Now, what has been thought about and determined over time is using this error in a constructive way in our controller. And so what we're going to do is we're going to make a controller now that includes what we call an integral term. And so we're going to now have a Kp, which is our proportional term, which is what we typically think of as our gain, but we're also going to add a Ki over S, which we know is an integrator, and we're going to sum those together, and then we're going to feed that to our system and then do a feedback. Now, this integrator term in here will work. Remember, we're talking about the error in here, this error. And so our integrator term is going to work on the error in here. We have a little bit of error. That little bit of error is not enough to cause our Kp to drive the system forward. But what happens when we integrate that little piece of error over a long period of time, or even a relatively short period of time? This error sums. And so the sum of that error builds and builds and builds. Eventually, the signal from our branch from the Ki over S gets large enough to drive the system onto the set point. Okay, so it actually uses the error to summing the error to close the system together and get a zero steady state error. And this is the big claim to fame of the integral term in a controller, is that it minimizes or reduces the steady state error. Let me show you an example here using MATLAB. Here I've got a little script set up, and all it does is create exactly the system that I was talking about with a Ki, just a first order system in there. And we can see here as we move this controller back and forth, I think I can do this, as we move the slider back and forth, what you're going to see is that as I move this down, let's turn the gain way down in here, and there we go. Now we see this error in here. Our set point is 1. We've got an input of a step response, a unit step response, or unit step input. But our steady state value is 0.9 or something like that. And so we've got this steady state error. Now I can crank the gain up, just like I was showing you. And I can reduce that steady state error, but it's still there. You can see that little gap in there that is still a steady state error. These two are not converging exactly. Now I'm going to switch over here to use CISO tool and simulate this system. And so here we have the same thing. I've got my step response to the system, and I've got my root locus. The little pink dot in there is my closed loop pole in here, and so I can move that around, and I'm essentially changing the gain on the system. So I can do the same thing in CISO tool, and I can change the gain, increase the gain. I can reduce the steady state error in here, but I can never quite eliminate it. And so what I'm going to do is I'm going to pull another pole in here. CISO tool allows me to put a pole on here, and I'm going to drop a pole in here, and I'm going to do a little bit of manipulation to that pole. In here, my controller, look at my controller, open the section, and look at this, and I'm going to put this in here at 0. I'm going to put that pole right on the origin. Okay. Now that gives me a pure integrator in addition to the system. Now look what happens. You can see that the steady state error has dropped to 0. It comes up here and it converges on our set point of 1. And now I can increase my gain and improve the performance of it a little bit. And if I come in here to critically damp. That's the best I can get without an overshoot. But I've always got a zero steady state error with a step input for this first order system with an integral term in my controller. And so very nice feature if you're looking to reduce the steady state error. Now, it comes at a price. Everything comes at a price in controls. It comes at a price, and it slows the system down. Okay, so if you're interested in speeding the system up, we're going to have to do something different. But if you are looking at reducing the steady state error, you should be thinking about adding an integral term to your controller. Okay, so we'll get into this a little bit more and do some calculations and get some details on this.